Okay, we'll get started again. Okay. Uh, Good morning, everybody, once again. Um, and today, what I want to do is, let's see, yesterday we talked about the waveforms themselves. Now we want to build banks of waveforms for our match filter searches. So I'll talk about banks of waveforms. I'll talk about the match filtering itself. And then I'll start to talk about a little bit about specifics of the pipelines that we use. This is very software dependent. So the way they are implemented for computational efficiency, the PyCVC and GSDLL take very different approaches for computational efficiency. And of course, speed. Just there's two aspects. One is how many computers you're using, and number two is even with enough computers, how quickly can you get an answer after the gravitational wave passes the detector. And we're aiming for on the order of minute scale latencies. So computational speed and latency are two different things. Keep them separate in your mind. And then I'll spend some time, if probably not till tomorrow, but we'll see, to talk about the challenges associated with the non-Gaussianity of the detectors and how we think we're doing pretty well at battling those. But as you can imagine, as I showed you earlier, as the mass of the system gets larger, the merger frequency falls like 1 over the mass. And we go to lower and lower frequencies within the LIGO band. And eventually, of course, the mass gets so large, or it's redshifted so much, if it's in cosmological distances, that it falls out of the LIGO band at low frequencies, and you don't detect it at all. But in between, when the highest masses that are still in the LIGO band, those are very short duration signals, and they look more and more like glitches, or more and more like short duration bursts that are just a few wiggles, like a sine Gaussian. And as we approach those higher and higher masses, it's just as easy, let's call it, to find those signals with burst type methods. And it's just as hard to distinguish them from non-Gaussian fluctuations, glitches, or other kinds of short duration detector misbehavior. And so we reach a certain point where it becomes increasingly hopeless, actually, to detect these things with glitchy detector data. And you'll see where that happens. Okay, so I talked a little bit about just an introduction to the pipelines themselves. In the past, long before in advanced LIGO, in the 10 years that we operated initial LIGO, all of our analyses were offline. Sometimes months after we took the data, we had everything tuned up and everything made sense. We ran all of I'll talk about how we measure our signal efficiency and our background estimation. These are the two things that any pipeline has to address. How well do we detect signals? How bad the background is to our signals from instrumental noise that makes accidental coincidences. But now we do it, as quickly as possible because, of course, we've been doing this for many years, and we know how to, in a reasonably confident way, estimate our signal efficiency and background estimation before we even start a run. So it's all set up and ready to go. Okay. Of course, detectors have a way of being not just non-Gaussian, but also non-stationary and producing new kinds of glitches. And the reason why that happens is because in between every one of our observation runs, we open up our vacuum, we replace mirrors, we change things, we change, connect and unconnect and reconnect cables. And when we turn back on again, we sort of have a new detector. More importantly, we are aiming to improve the sensitivity of our detectors more and more and more. Okay? And if, just schematically, as a function of frequency, our noise curve looks like this in one run, we may not notice a whole set of misbehaviors producing noise an order of magnitude below. And then we improve our sensitivity, and all of a sudden we've uncovered a new noise source that we've never encountered before. Okay? And that happens over and over and over again. Okay? And when we do uncover such new noise sources, we're not ready for them. We have to figure out what they are and figure out how to fix them. So we have to be light on our feet. Okay, so again, I'll concentrate on two detector coincidence. We have yet to make any claims that we see a signal with a single detector, a transient signal. Okay, we can, as I mentioned earlier, detect continuous waves from spinning neutron stars with one detector with great confidence once we have enough signal-to-noise ratio, but we can't do that with transients. There's just too much glitchiness in the data. But if the signal is loud enough that it really does look like the kinds of waveforms that we're looking for, we're going to start claiming we see something. And the reason why we need to do that is because with two detectors with duty cycles of 65-70%, coincident duty cycle is 50%. There's a significant amount of time when we only have one detector up. And we don't want to lose that information. Certainly not if a supernova goes off during that time. Okay. Okay. So let's start with template banks. Okay. So we know that, well, we'll talk about match filtering shortly, and we know that you can do a match filter search with a single template on noisy data, and if that template is rung up by something in that noisy data, we have a potential signal there. But each one of our waveforms is parameterized by masses and spins, and so what we're going to do is make a bank of a whole lot of templates. So here's such a bank. You've probably seen it before. Here is, on a logarithmic scale of all things, the mass of the larger mass system. Larger mass in the binary. Here's the smaller mass in the binary. I guess you can call this the primary and the secondary. And here, so this side is unphysical because that would be M1 less than M2. And there are three regions. The region from 1 to 2, or maybe 1 to 3 solar masses, is the binary neutron star region, where both of them are in that region. And this is an arbitrary distinction. If you come and tell me, there are binary neutron stars that that live here, or there are binary neutron stars, there are binary black holes that live here, I'm not going to argue with you. This is just nomenclature. Let's call it that for the time being. This is our binary neutron star region, neutron star black hole. I think nowadays the trend is to call them black hole neutron stars, bigger versus smaller. I don't know. It's up to you. But nowadays there's a trend. BHNS rather than NSBH. This is the binary black hole region. Again, just nomenclature. But there is a difference. There are important differences. This is the region, and it doesn't go all the way out to here. It goes out to maybe 10 or out to maybe 20 solar masses on 2, where you expect that the merger will produce light and lots of light, and therefore this is what we call electromagnetically bright region. And this is where it's most important to be fast on our feet and tell our telescope partners around the world, hey, point here. It's somewhat less important here. Of course, there's an industry now of people looking for mechanisms by which binary black hole mergers could produce some light. All kinds of interesting ways using, you can get all kinds of currents flowing and producing pre-merger flashes of light or post-merger flashes of light through all kinds of creative mechanisms. Those are the kind of creative mechanisms that are pushing the envelope. In other words, they're unlikely to be really true. And even if they are true, we typically detect gravitational waves from binary black holes. Here again, here it is on the linear scale, mass 1 to mass 2. And these contours are contours of sensitive luminosity distance, okay, which you're going to calculate in the problem set that I gave. Okay? And what you see is that, of course, the sensitive distances are hundreds of megaparsecs for more massive stars, and only 50 or 200 megaparsecs for the lighter ones. Okay. So typically, a binary black hole is expected to be very far away. And if it makes a little bit of light, you probably won't see it simply because it's too far away. So that's why it's less important, but we still do it, to alert people to binary black holes quickly, optical telescope operators quickly. It would be a great discovery if we found some light from a binary black hole merger. The next thing you see, again, this is a logarithmic scale. It goes out to 100 solar masses now, but we are extending it to 200, 300, 400 solar masses because there's still some, that's at lower and lower frequencies, but optimistically there's still some signal-to-noise ratio from those signals. There's still some in the LIGO band. So there's a whole search dedicated to understanding, to looking for these much higher mass systems, IMBH, right, intermediate mass binary black hole systems, but they are, but they have to really fight the non-stationarity, the glitchiness that shows up at low frequencies for very short durations. That it really collides with the signal you're looking for. So it gets harder and harder. So this is our O1 bank, and we've expanded it to 250 solar masses max and I'll show that to you for the O3 run. Okay. Yeah.
One thing that I have seen this plot before, and I'm curious about why do you have less template in one region than in another one? Why you wouldn't try to complete as much as you can?
That's what I'm going to talk about next. Okay. So next, why is it that the number of templates are much, much denser here than they are here? So let's try to understand that. Again, this is just what I said before. We want to be able to detect any signal in a large parameter space, but with a finite set of templates, so we build a bank of templates. Now, our goal is to make sure that those templates are placed close enough such that every part of the signal space is covered at some level. And we require a minimum overlap between signal and template of some amount, let's call it 3% or 97%. That means that if you throw a dart and pick a random place in this template bank, it won't hit an actual template, but it'll be close enough to nearby templates that those nearby templates would pick up that signal with at most a 3% loss in signal-to-noise ratio. And that corresponds to a loss of 3% cubed in the amount of sensitive volume, or a 10% loss in rate due to the signal-to-noise ratio getting smaller, losing signal-to-noise ratio by not hitting a template directly, because you never will. Throw a random number, you won't hit one of our templates, but you'll be somewhat close. So what we want to do is compute the distance between any point in this template bank and any other point in this template bank in which we might have placed a template. So that's our goal. Now, what we'll see is that in some regions, the in-spiral region of the template bank, one can define and calculate a metric in the space M1 versus M2. But at larger masses, we cannot. Here's why. For a binary neutron star, it merges out here at 2 or more kilohertz. We typically expect that our signals, well, they come in at f to the minus 7 over 6, and then they merge. And we typically expect that for far enough, if it's very close, that merger will be inside of our noise curve, and we'll be able to get some signal-to-noise ratio out of it. As I'll explain later, the signal-to-noise ratio is essentially the area between this signal curve and the noise curve, signal-to-noise ratio. Okay? It's the area. So over here, there's no area. It's negative. All right. The way I drew it, it's negative. So there's no appreciable signal to noise. So it's essentially in spiral only templates. And that's true for all the low masses. Right over here, all these are going to be modeled with in spiral templates. Now, in spiral templates, especially the to lower order in post-Newtonian expansion, have a metric in this parameter space. Yeah, you can flip. Yes. We can use the same templates all the way along here. The reason why we like to use in spiral only templates here is purely technical. As far as I know, you can perfectly well use the others, but the technical our in spiral merger ring down. But the technical reason is that much effort has gone into these phenomenological template waveform models, phenom B and SEOB and R, tuned to numerical relativity, and all the effort has focused on tuning it at higher masses. And very little effort has focused on doing it at lower masses. Oh, I mean, uh, along a diagonal line, you can use one numerical relativity template. Well, not one template, one template rescaled every time. They have to be rescaled. You can see that one of our template bank strategies is to first populate the diagonal line. You can do that with one numerical relativity run, but every one of these dots is a different template for a different mass. So to a numerical relativist, they don't care about what the mass is. They don't care what the frequency is. They can make a template that works for Lisa at millihertz frequencies, or LIGO at kilohertz frequencies. They don't care. We care because we have a noise curve. All right. General relativity might not have a scale, but we do. Our scale is set by our noise curve. So we need separate waveforms for each. Does that address your question? So, yeah. Why are there what? Oh, yeah, there are, aren't there? 2 points for the LVT. And that is because we have two pipelines, GST-LAL and PyCBC, and lo and behold, they detected it with different templates. And that's telling you something. Okay? It's telling you two things, first of all, that the wave templates here and templates here have considerable overlap. Okay? Also, the considerable overlap when they are in the noise weighted, in the sense of noise weighted overlap, which I will define shortly. Still, there's lots of templates in between. The overlap between here and here might be 97%. The overlap between here and here might be 90% or 80%. Okay? But at low SNR, you don't necessarily tell the difference between two SNRs that are well above threshold, that are have noise fluctuations that can just absorb that, and different techniques for doing the signal processing can cause it to be found in two different places, and that's telling you something. It's telling you how accurately you can measure these masses. Yes. That doesn't mean they're optimized for that. They're not. They're optimized for having efficiency that's flat across the entire template bank. The reason why these are more dense is because templates are closer together here. So this is what I'm going to try to explain to you. And why are templates closer together? Here, under this requirement, a loss of no more than 0.97, the templates have to be placed closer together here. Why? Because why? No, it's not because of spin. Spin has something to do with it, but there's a higher order effect. Because of what? No. Longer waveforms, more cycles. When you have more cycles, and over here we're talking 5 cycles in band, and over here we're talking 5,000 cycles in band, and the number of cycles in band goes like 1 over the symmetric mass ratio. Here, the symmetric mass ratio is 1/4. It's dimensionless. It's symmetric, which means I don't have to tell you whether Q is M2 over M1 or M1 over M2. And I can tell you 50% of authors use 1 and 50% of authors use 2. Okay? I'm not even kidding. It drives me crazy. This one, it doesn't matter. Okay? And it's equal to 1/4 if M1 equals M2, and it's less than that, and can go all the way down to 0 if Q, defined this way, approaches 0, in other words, extreme mass ratio, then eta is 0. So eta approaches 0 for extreme mass ratio. Okay? The number of cycles, something that you can derive from the problem set that I gave you, the number of cycles is proportional to 1 over eta. In fact, I showed you that the chirp time is proportional to eta. Okay? So at high mass ratio, it takes a lot. It is a lot. The chirp mass is much smaller. Chirp mass is the total mass, m1 plus m2 times eta to the 3/5 power, which means gravitational radiation is weaker, which means the in-spiral is slower, which means that it spends more time in our band. Make sense? So this template here and this template very nearby have thousands of cycles in band. And if you're off even by a little bit, you're going to go from, here's thousands of cycles of one template, and here's thousands of cycles of the other template matching beautifully. After a while, destructive interference. You just lose the signal-to-noise ratio. Okay, does that make sense? So that's why you need to space the templates much closer. And now I'm going to show you a little bit more about how this works, because it's mathematically elegant in this region and a little bit more complicated in this region. In fact, if you look closely, which you can't in this plot, but I'll show you in another plot, in this region, the templates are spaced in some kind of a grid. And in this region, they seem to be random or stochastically placed, which is exactly the case. Okay, let's see how it works. Of course, what we want to do is minimize the number of templates while still covering the space as best as we can. We want to minimize the number of templates. Why? Because when you take one data stream, h of t, and send it through one template, you get an output data stream. It's usually called z of t. It's complex because it's this convolution. We take both the cosine-like and sine-like parts because we don't know what the phase is. So this is an efficient way of optimizing or maximizing or covering all possible phases between, the signal and one of the templates. We don't know whether it starts like this or starts like, this, sine-like or cosine-like. So we try both by doing a cosine-like term plus I times a sine-like term, and then our match filter will give a complex output z of t, and its magnitude is proportional to the signal-to-noise ratio, as I'll show you. So the input goes to the output. This is a time series. This is a time series. But if you have more than one template, if you have n templates, you end up with n time series. Okay? So H of T comes in, template bank, 600,000 templates in O2. It'll probably be a little higher in O3. 600,000 time series out. This isn't data reduction. This is data explosion. Okay. The first stage of our processing pipeline, match filter processing pipeline, is a data explosion. In fact, at this point, we can no longer even store all that information. It's just way too much. So we have to throw it away. And then we do that by looking for peaks in this and just registering the peaks. And I'll show you how that works. Okay. And so I think I said all that. One way of thinking about it is that think of, let's say we take 1 second of LIGO data and it's sampled at 16,000 hertz, 16,384 hertz. That's 16,384 hertz samples. Every one of those samples can be anywhere from minus infinity to plus infinity. So think of it as as being 1 point in a 16,000 dimensional space. Okay, 16,000 dimensional space. And I don't know how to draw 16,000 dimensions here, so I will draw 2. Okay, then I have a template, and the template is one particular point in that space. Okay, if the template is good GR, it lies where I want it to be. If it isn't good GR, it's going to lie somewhere else. Okay, if I got the GR wrong, if I got the computation wrong, made a mistake, it's somewhere else for those parameters. But consider the space of all possible waveforms in this space. There are a bunch of points. Not just because we have a finite number of templates. Even if you allow for an infinite number of templates, they still only live in a finite sub-manifold of the full manifold of the data. Okay? And most of the data is noise. It's other points in this space that wouldn't correspond to a waveform, or to any of our waveforms, not just the ones in our template bank, but any possible CBC waveform. There are certainly, you can imagine, regions of this 16,000 dimensional space that are simply empty of signal. Okay? And the whole point of a template bank is to ignore those regions. And those regions are much, 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 much more volume than the regions where the templates are. So thinking in abstract linear algebra, we are looking for tiny, tiny subregions in a very large 16,000 dimensional data space, subregions in which there's signal. Okay, it's sort of like looking for those little holes in Swiss cheese. So that's why we call this LIGO cheese. So we're looking for those little holes in that Swiss cheese, which are places where real signals can live. Okay? And what we want to do is throw away all the rest. They won't match to any of our signals in our template bank, or even close. So that's how you want to think about it, as reducing the abstract linear space that that filtering allows you to reduce by a vast, vast, vast amount. I mean, right? This is a vast reduction in volume. Yeah. Right. Only. Only. Remember I mentioned ye old chicken and egg problem. Let's say nature isn't obeying GR, and our signals are really not GR-like. If they're a little bit different, they still might overlap in this LIGO cheese with one of our waveform templates. And then we'd at least find it, maybe with an SNR of half, because we really got it wrong, because nature is nothing like GR. We really got it wrong. Still, if it's a loud enough signal, even losing half of the SNR, we might still pick it up. And then we analyze that signal that we picked up, that tiny little bit of our 6 months of data that lasts for a second. We at least identify it. And then we can throw a lot more power at it. Does it look like? Allow the templates to vary away from general relativity. That's a much, much bigger space to explore. And we can't do it for 6 months of data, but we can do it for a fraction of a second of data. Right. We have a name for it. Testing GR Tiger. And you will find that we have several papers in which we apply this to in all of our discovery papers. Every time we discover something, we run our little TGR um, uh, uh, um, uh, beyond general relativity with templates in which we allow all those post-Newtonian coefficients, those 73-digit integers, allow them to be anything. Right. And it's a lot of extra parameters, and it takes weeks or months to get convergence. But we do, and then we find, ha ha, it looks like GR. So far, first 6 events, they all look like GR. Of course, the most important event is the binary neutron star event, because that has so many cycles of in-spiral in band that we can really constrain GR better than any of these others in the post-Newtonian part of the waveform. But of course, all these others, higher mass ones, probe the merger and ring down. So there's lots to play with here. Okay. But it's a chicken and egg problem. If the signals really are so different from GR that our waveforms don't even pick them up, we'd never know. So I got to tell you, I was one of those people who was holding their breath on whether, we will pick up our signals with the templates we've got. But I was comforted by the fact that high enough mass systems will have so few cycles in band that even if GR is wrong, we're going to pick up something. And in fact, that's the power of the burst search that Marianne will tell you about, is that it's GR agnostic. It's not based on GR at all. Any kind of wiggles in the LIGO data, it'll find. But if there are lots of wiggles, then it'll find it with far less sensitivity. Because if you can do constructive interference on many, many, many wiggles, the SNR builds up a lot. Whereas if you don't know what all those wiggles are, you're just looking for excess power. So it isn't being constructive interference. Instead of adding up the amplitudes from time period 1 and time period 2 and time period 3, adding them up, if time period 1 is 161 microsecond period, and then you add up to get a whole 61 seconds or something, you'd need 1,000 of these. This is what matched filtering accomplishes. Burst searches add in quadrature. Add the power in adding up the power, and then the total amplitude is the square root of that. So you're adding these things up in incoherently as opposed to coherently. So a matched filter is coherent. Burst type searches looking for excess power are not coherent, although you can make them more and more coherent by fiddling around with your burst search algorithm, but you're not using GR. And Marianne will tell you how you can fiddle around to make it more coherent without even knowing what the waveform is. Does that help? Okay.
I'm trying to get a handle on this sort of manifold space.
Yes.
So then if I looked at 2 seconds, it's a 32,000 dimensional space, et cetera, et cetera.
Yeah.
If I think about a pure sinusoid in time, where those values are large, it's some set.
It's 1 point.
Really one.
Yeah. In this dimensional space, that's right. And if you want to get all possible sinusoids, okay, then it's a lot of points. But they're a very, very, very small subset of the total space. The rest is all noise. It's all noise. Okay. So what you got to ask yourself is how close 2 templates or 2 points in parameter space are to one another. You can define this quantity over here, which is this inner product is a noise-weighted inner product. It's easy to calculate in the frequency domain, so we usually do it in the frequency domain. In the time domain, it's a little bit more complicated. Okay. So here's waveform template number 1 and waveform template number 2. This is their complex Fourier transform. This is the noise power. So it's a noise-weighted thing. When the noise power is high, this integrand is small. It's just not going to contribute to any signal-to-noise ratio. When the noise power is low, this integrand hopefully will be high unless there's destructive interference. And so that's why this is a signal-to-noise ratio, a measure of the signal-to-noise ratio. Okay? If this were noisy data and this were a template. Instead, you can choose two templates, 2 points in parameter space, and see how well they overlap in this noise-weighted sum, okay, or integral. Here's a subtlety. I drew 2 templates over here. I guess I erased them already, which were 2 wiggles that were slightly different from one another. Here's one. Here's another. It looks pretty good for a while, and then it starts to deviate, and all of a sudden, after a while, it becomes destructive interference, and you start losing SNR, so it's too far away. But of course, I could have taken this template and moved it by pi over 2, and then it would be completely off, wouldn't it? So if nothing else, when you look at 2 templates in the time domain, you have to time shift them until they line up as best as you can get before you evaluate this. Okay. Now, a time shift in the time domain corresponds in the frequency domain to multiplying by e to the I 2 pi f times that time shift, delta t. Okay. So I can take this factor. Remember, this is complex. I can take this factor and put it in here, and then my integral becomes an inverse Fourier transform. And my inverse Fourier transform becomes in the time domain, a time series in delta t. And then I just look for a peak in that time series. And that corresponds to maximal overlap. Another possibility is to assume that this quantity here is complex because of this thing. Well, also because those Fourier transforms are complex. And its magnitude is going to give me the peak. It won't tell me where the peak is, but it'll tell me that there's a peak somewhere. So this is the wave function or waveform overlap. It's not normalized, of course. I can always make it bigger by taking the waveform and multiplying it by 10. Right? Or anything. Because our waveforms are, normalized by how far away they are, and I haven't, the template bank doesn't know how far away things are. Okay. So I need to normalize it. So here's a normalization. So now, if you multiply either of these waveforms by any arbitrary constant, it cancels out between numerator and denominator. So this is the waveform overlap function. So now we need to know, if I have 2 points in parameter space, what's the waveform overlap function? Well, what I can do is take a point in parameter space and take other points nearby and calculate this quantity. And as long as it's greater than 0.97, I'll keep it, otherwise I'll throw it away. And lo and behold, I find an ellipse, an ambiguity ellipse. Okay, yeah? I haven't told you what this or this is yet. Templates what? 3%. Yeah, that's a hard thing to swallow. Oh, if I would have picked 0.975, I would be better. But I would have more templates. I would need more computers, and that would need we need more electricity, and then I'd have to go to the NSF and say, give us more money, and they would say, no. So it's an optimization thing. And that optimization has never been looked at deeply. It's probably possible to argue, I don't want to live with 10%. I want to live with 6%, so a 2% loss. I want this 0.97 to be 0.98. That'll mean it's going to go up very quickly. It'll mean, 2 million templates rather than 600,000 or something like that. Do we have enough computers? Go down the hall. Hey, Stuart, do you have enough computers? Yeah, go ahead. We can afford it. We should do that. Right now, we're just working on inertia. We've always used 0.7. Let's continue to use 0.7. Bad answer to your question, isn't it? Oh well. Okay, so once you have an ambiguity ellipse, you can stack them close together. Those ambiguity ellipses you'll see are elliptical. They're not circular. They have this funny shape. But it depends on what you're plotting them against, which I'll talk about in a second. And so you but still they'll have some elongation, and when you stack them, you need to find an efficient way to stack them. In this plot, those ambiguity ellipses are approximated by little rectangles, and then there's a regular grid of templates spaced that way. In other words, what we've done is determine. Here's the key point of this. The key point is that in this parameter space, these ellipses all have the same size and orientation, same size and shape. Why? It's because when I take F1, M1, and M2 in my parameters and transform them to tau 0 and tau 3, tau 0 is the chirp time that Ilya calculated that I showed you. And tau 3 is the next post-Newtonian correction to it. And tau 0 can be many seconds, and tau 3 is typically smaller than that. Okay, because this first next order post-Newtonian correction to it is smaller. And you can show mathematically that in that post-Newtonian approximation, in these parameters, not M1 and M2 obviously, but in these parameters, the metric is flat, constant across the whole space. The shape of the boundary is weird. It's this weird shape. This is equal mass, and this is unequal mass. This is the extra time associated with asymmetry in the symmetric mass ratio. It's less than 0.4, less than 1/4, and it goes like 1 over eta. So here's more asymmetric masses. Here's the symmetric mass case. And within this weirdly shaped boundary, I have another plot that shows the whole boundary for the BNS region. Here. This is the whole BNS region. You have a flat metric, and you can just do a grid of points in that flat metric spaced equally. And again, because they're elliptical, you space them close in this direction where they're bumping together, and far in this direction where they're more elongated. So two things. First is that they're calculated from the overlap between a template here and another point. Another point. So within this ellipse, every other point overlaps with this template by 97% or greater. That's numerically. But analytically, you can do this all analytically and compute this metric in tau 0, tau 3 space, and compute these ellipses very quickly. Because in second order post-Newtonian, this is 3.5, this is tau 3 is the 3/2 post-Newtonian extension. You can really just the next term beyond the lowest order Newtonian, post-Newtonian. The next term, the first term has no dependence on eta, and the second term does. So you can, it's elegant math that I'm not going to share with you, but there are plenty of papers that you can read about it that derive what that metric is in this space, which is formally equivalent to M1, M2 space. Every point in M1, 2 space matches to a point in tau 0, tau 3 space, uniquely. It just distorts the space dramatically, resulting in a space that has a flat metric as measured by the distance between 2 points. Yeah. No, not for a flat metric, and not even for higher order post-Newtonian, and certainly not for IMR. For in-spiral merger ring down, there's no longer a flat metric. There's no longer an analytic form for the metric, flat or not. And now you have to actually numerically compute overlaps. Okay. Which is why I said that in this region of parameter space, the BNS and NSBH, which is dominantly in spiral, we can use a flat metric and compute the template bank and put it on a grid. You can put it on one of those like rectangular grids, or people like hexagonal grids, because hexagonal grids generalize to n dimensions very elegantly. But you don't need to generalize to n dimensions because of your question and my answer to it, which is that when you go to more dimensions in parameter space, include spin, you don't have an analytic form for the metric. So the hexagonal placement doesn't help that much. And out here, we have to resort to numerical methods. Yeah. Very good. Very good question. Another place where I have to be just a little bit unsatisfactory in my answer. Non-stationarity means that this is changing with time. In initial LIGO, we took the trouble to compute the SNR, compute the power spectral density every hour, and then compute a new template bank every hour. But in advanced LIGO, we stopped doing that. And we stopped doing that for a couple of reasons. One is that it just was, we found that the variation in the template bank changed this minimal matching from 0.97 to 0.965. It just wasn't worth the effort. It's easier to just go to point, to start with a minimal match of 0.975 and allow the variation in the PSD to bring it down to 0.97. So that's one answer, but there's another answer. Oh, and by the way, I'll mention to you that this power spectral density or amplitude power spectral density looks like this. You can see, and it varies by an order of magnitude in the LIGO band, and by many orders of magnitude outside of the LIGO band, up. But in this region, which we call the LIGO band, from say 20 hertz to 2 kilohertz or 4 kilohertz, it varies by an order of magnitude. It is what we call colored noise, because white noise would be flat in power spectral density as a function of frequency. What happens is that if you take this noise curve and translate it up or down in this logarithmic space, it makes no difference because everything's normalized. Okay? But if you change its shape, it makes a big difference. The flatter it is, the more templates you need. And the more colored it is, the fewer templates you need, okay, to cover that space. So the only time we might really need to rebuild a template bank is if the noise curve changes a lot, maybe much more flat or something like that. In shape, not just height, The height doesn't matter. Shape. Okay? And that doesn't happen that much over the course of months. Oh, yes. Oh, yes. Absolutely. Between O1 and O2, between data runs, we rebuild our banks. No question about it. But here's the real reason, and I'm jumping ahead. Coincidence. So in initial LIGO, we said, I have two signals, and one in Hanford and one in Livingston, and I have two different banks because they have two different noise curves. And now I need to know whether these signals are coincident, not just in time, but also in parameter space. Oh, laborious calculations. If you make exactly the same template bank for both Hanford and Livingston and ignore the fact that the noise curve is significantly different, because it isn't, but for Virgo it is, but if you ignore the fact that the noise curves are different, then all you need to do is require that the signal is found in exactly the same template in both detectors. Turns out to work just as well for much less work. So that's the real reason why we don't sweat too much about non-stationarity or even the difference between those noise curves at different detectors. Turns out, numerically, just when we do our injections and our background, we actually win by requiring that the templates be identical in all detectors. So once we've laid out our template bank in a region where we have a metric, again, we can do it on a grid, we then have to worry about what happens. So here's what the template bank looks like, retransformed back into M1, M2 space. And this corresponds to these two types of template bank space placements, blue and red, cover the bank equally well. Equally well. And as you get to large values here, the spacing, the ambiguity ellipses, these are the ambiguity ellipses here. Sorry, not a different template bank. These are ambiguity ellipses. They're long and thin in this direction. And so typically, the template bank is placed, it doesn't look orthogonal, but in the other space, tau 0, tau 3, these two curves are orthogonal to each other. That is to say, the template spacing is tight, close, in the direction orthogonal to this ambiguity ellipse. And each one of these templates corresponds to another ambiguity ellipse stacked very closely together. And there are different ways of laying the banks out, hexagonal and square, and all kind. And there's still always a bias towards equal masses. So we tend to do equal masses first, and then do all the rest. Okay. Okay, but in higher dimensions, like adding spin, or if the metric is either, it doesn't have to be flat, but it has to be known analytically to make this work well. But if it's unknown or complicated, then instead we apply stochastic methods. What does that mean? That means, let's see, that means that up here we put down a template and then we throw a dart, find another random point, randomly, stochastically, in the parameter space. Calculate the overlap. If it's less than 0.97, keep it. If it's greater than 0.97, discard it. Repeat. Takes hours. You are left with the possibility that you haven't converged, that there may be little voids that your dart just never hits, but that randomly, but are not perfect coverage. So you got to run it for a long, long time. And then you got to give over coverage, require over coverage, and then you can back off a little bit. That's how you build a stochastic template bank. And that's what we use for most of the parameter space. Does that make sense? Okay. All right, so that's template banks. Here's a question you might be asking. because I did the first time I learned about this, and that is you're taking these templates and putting them very, very close together. Okay? We're covering 97%. These templates are very similar to one another. True, if you integrate over enough cycles, they become dissimilar, but they're pretty darn similar to each other. So you've got a lot of redundancy in your template space, a lot of overlap. It seems like you're doing a lot of, it's brute force. You're doing brute force, lots of extra computing work, okay, it's just computing, to require that coverage using templates that are almost the same, only slightly different. In fact, only a very small fraction of them are independent of each other. Okay? So you could imagine I'm going to take each template and decompose it into independent basis templates so that I can add them up and get template 1, add them up in a different way with different coefficients to get template 2, all the way up to the 600,000 of them. Okay? There's a standard numerical approach for doing this. It's called singular value decomposition, SVD. You can take your 600,000 templates and SVD them, and it will give you a much smaller set of basis templates, which then you can add up with coefficients that are predetermined to get any template you want. And that works within a region of parameter space that it works in. And if you extend to some outside that parameter space, it won't work. You need your basis templates will be a small, must live. You try to make sure it, to a large extent, spans the entire parameter space you're looking at, but it certainly won't span any points outside of that parameter space. Does that make sense? Linear algebra. So, and this can save a lot of CPU time. And it turns out that although we don't bother to do anything like this for PyCBC's slower offline analysis, for the GSTLL analysis, which I'll try to describe shortly, it's optimized for low latency in the time domain, and it requires this SVD because then you only filter through a much smaller subset of independent templates, get some answers, and then add them all up after the filtering. Okay, because the filtering in time domain is a lot slower than filtering in the frequency domain once you've already done your fast Fourier transforms. So that's a very important technique that's used in GSTLL. And it's, as we have many more templates, much longer waveforms, much larger template spaces, more complicated waveform families, this kind of thing is actually essential. This kind of speed up is essential. This is one singular value decomposition, SVDs, is one example of a much, much bigger applied mathematics field called reduced order modeling, ROM, reduced order modeling. Turns out to be an extremely powerful, beautiful, and elegant technique in linear algebra for taking a complicated system, 600,000 templates, and reducing it to a much, much smaller, simpler system through linear algebra. You can add back up to where you want, to your more complicated system. SVD is the simplest. It's the only one. The only thing in reduced order modeling that I understand is the SVD. But it is much more deeply explored in applied math and signal processing. And it has one interesting hidden advantage. Your templates are GR templates, and they're spanned by these SVD decomposed independent waveform template basis vectors. There's some non-GR stuff that might be going on that we don't know about. If you're lucky, your SVD decomposition will cover those too. That's the upside. It covers more than just the signal space that you've predefined. The downside is it covers more of the noise space. Pulls in more noise because you have more degrees of freedom. Non-GR, oh sure, bring in your elephants. Um, it's a downside. If you can tolerate it computationally, you do, and we do. So we're a little bit looser in our GR requirement when we do our SVDs. Okay? We let in a little bit more of the noise part of the cheese. At the that's the downside, and the upside is we can pull in signals that aren't precisely GR-like. Does that make sense? Okay. Reduced order modeling is now used way beyond SVD. And it's used in two places, at least. It's used to interpolate between different templates. I'll talk about that shortly, but well, I'll talk about it now, I guess. Remember I said that we use these phenomenological families of templates, which are tuned to the numerical relativity waveforms, of which we only have dozens, and we need 600,000 of them. So they're tuned in those regions, and we assume that they interpolate between those handful of, of numerical relativity waveforms smoothly and more or less accurately. And that's what SVD will do, and that's what these fancier numerical reduced order modeling techniques do. Interpolate between different waveforms in between in parameter space. So if one day, and that one day will come in the next few years, we're going to throw away all these phenom Bs and phenom Ds and phenom thises and that's and SEOB thises and SEOB that. We're going to throw them away. We're going to go straight to the numerical relativity waveforms and interpolate between them using reduced order modeling. And we know how to do this approximately. It's under development. It's an interesting problem. Does that make sense? So we're going to do that. It's going to take a couple more years, I think. Actually, yeah, okay. But the problem with that is that the numerical relativity waveforms are dominantly either spinless or aligned spin, and we have very few precessing or non-aligned spin numerical relativity runs. Very few. So interpolating, you worry that you're not doing it right. That's the problem. Okay. It makes a difference, of course, because different regions in parameter space produce very different waveforms. And the flip side of that is that very different waveforms tell you what the parameters are better than, the more different the waveforms are, the more power you have to measure those parameters. Okay? So here's 3 waveforms. They all have total mass of 10. This one is equal mass. It's blue, nice and smooth. This one is unequal mass, much longer waveform. And this one has spin, and I can see that it has non-aligned spin because there's precession. And the precession means as this orbit, the binary orbit, wobbles or precesses, sometimes it gives you more plus and less cross, and sometimes the reverse as it precesses. And your antenna patterns see plus and cross differently with different responses. And so you'll see a louder signal, a weaker signal, a louder signal, a weaker signal, a louder signal. You see this amplitude modulation. Okay? And that amplitude modulation is telling you you've got spin. It's not coming from the source. It's coming from the detector, response to the source. Okay? As the polarizations change due to the thing wobbling. Yeah.
And why the final stage is later when you have spin?
It all depends on where you start, and we start at a certain, and this is a time domain, but it's starting actually at some fixed frequency, 20 hertz, or I don't know exactly how this plot was made, whether it was, I made it probably a very, very long time ago, like 20 years ago, so I don't know. But the point is that you start at some fixed frequency, and then you have a lot longer time in band because of that 1 over eta in here, okay? Which is in tau 3. Tau 3 is only important for the last stages. These are the last stages. Don't forget these waveforms extend out to minus infinity, or billions of years, let's say, or maybe 10 to the 14 years. Okay, these differences, of course, are easy for match filters to pick up, which means you should be able to very well distinguish between these guys. Okay? You don't see it so much in the frequency domain. There's a little difference, but not a whole lot, because in the frequency domain, all I know how to plot is the magnitude of h of f. But it's the phase of h of f that has all the information. It's not on here. But you can see it with your eyeballs in the time domain. The actual templates we use are even more messy looking or complicated. I'm not going to, I'll apologize for this because I didn't decide this, but you know, my colleagues decided what's the most optimal way to lay out all my templates? Well, I'm going to do one sort of technique in this region, equal mass or close to equal mass, and another technique in this region. I'm going to cut this off here. This corresponds to very high mass ratio. 200 solar masses on 1 solar mass, a Q of 200 or 1 over 200. I don't know, that's why we have symmetric mass ratio. And eta very, very close to 0. Okay? In this region, we don't have reliable templates. Turns out nature doesn't seem to be giving us a lot of those anyway. But we don't have reliable templates. Why? Because and ask Harold Pfeiffer why. Okay, he's going to give a talk next week on numerical relativity. Hey, Harold, why don't you get us some high mass ratio templates? Sure. How many decades do you want to wait for them? Because these waveforms are much longer and they require much better spatial resolution to have a small guy orbiting a big guy. So if you're going to grid up your space-time foliations to do your numerical relativity, oh, you need many more points to resolve your little black hole orbiting your big black hole over large distances down in. Yeah. There are all kinds of, the in-spiral part you use the post-Newtonian. There's also other techniques, perturbation techniques in field theory that are under development that I can't speak a whole lot about. But I don't know if that answers your question. I mean, don't forget that when you go to this region, you're not interpolating, you're extrapolating into a region that you haven't even a single numerical relativity waveform ever generated. Now, you could argue, how weird can they be? How different can they be? But you're on shaky ground. Yeah.
By the way, if I remember these numbers right, for the Einstein toolkit numerical relativity code, the record is from Georgia Tech like 20 to 1, and I think it's about the same in SPEC.
Yeah, and this here is 100 to 1. We're already extrapolating using our Phenom B and SEOB and R waveform families that are tuned to numerical relativity in this region, and we're extrapolating into this region. Yeah. And in some sense, that's what EOB is all about anyway. Equivalent one body is supposedly rigorously accurate, I guess, in the sense of perturbation on Q or eta, in the limit that eta goes to 0. So SEOBNR is actual hard theory for high mass ratio systems. The way we use it is for more equal mass systems, and there it's not hard theory anymore. It's you got to take all the coefficients in SEOBNR and throw them away and replace them with fitted values that are tuned to numerical relativity in this region. So ironically, SEOBNR should work really well here, but we use it over here by turning it from being a rigorous theory into a phenomenological model. Yeah. Awesome. Awesome. And remember, we have very high density here. Okay, so maybe we'll get rid of this whole template bank-based approach and come up with a more clever way in the future. I say that nature doesn't seem to be giving us much of these. Of course, we wouldn't know because we have no templates there. But nature seems to be giving us practically nothing here. Well, we haven't seen an SBH. Okay. But whenever you say something like that, you can take it two ways. Oh, that's good, then you don't have to worry about it. Or, oh, that's terrible. You need to worry about that a lot. You're either doing something wrong or you have an opportunity to discover something. Very high mass ratio inspirals will be very interesting for us to discover. The more rare something is, the more interesting it might be to some people. So when I say, oh, we don't see any, so we're not going to worry about it, you can take the other sign on that. Does that make sense? Okay, now just a few slides on match filtering. I can tell that at least half of the room, if not more, already knows all this. And there are those of you who don't, so I'm going to spend a little time on it, just a little bit. Okay. Here's just the schematic of how it works in the time domain. So in the time domain, you have noisy data. There's a signal inside of it. It's very hard to see. Well, I colored it in black. Otherwise, I'm telling you, you wouldn't have seen it. You just wouldn't see it. Okay. Even at the merger, you just don't see it because it's smaller than the fluctuations in the signal. Now, mind you, this is, and I'll talk shortly about it, this is whitened data. Okay? If I hadn't whitened it, we would see gigantic low frequency fluctuations, orders of magnitude, well, at least one or two orders of magnitude bigger than this. But I'm suppressing them by dividing by this noise curve. Well, remember the noise curve is spelled like capital S of F is the noise power, and I also will refer, and that's called the power spectral density, and the square root of it is the amplitude spectral density. Okay. So when I draw this, I draw an amplitude spectral density usually, because these numbers are 10 to the minus 24, 10 to the minus 23, 10 to the minus 22. If I was drawing a power spectral density on a log-log scale, it would look exactly the same, except instead of this being 10 to the minus 24, it would be 10 to the minus 48. Okay? And when you divide by a big number, all those low frequency fluctuations get squashed. They all get squashed. And so this is already whitened data. And I'm not even including anything below 20 hertz because I'm dividing by a very large number below 20 hertz. Okay, here's the data. Here's the signal buried inside the data. Here's the waveform with all those oscillations. Here they are. How did I screw this up? Oh, I'm sorry. It's reversed in, there's a reason why it's reversed. But I'm going to, oh, it's flipped over as well. Forgive me. But in any case, the point is that low frequency here goes to higher frequencies. The merge and ring down comes from parameterizations of numerical relativity waveforms. Okay, and they're boring. Another cycle or two, and then the ring down. like I said, that we used to think that it would get really interesting due to spin hang-ups, but turns out there aren't any, at least in the regime that we're interested in. When the spins get to be 0.99, I wouldn't be surprised if spin hang-up shows up and turns into an interesting thing that you can observe, like a much more complicated waveform here, possibly. In any case, here's the waveform that we're looking for, and we have a bank of them, 600,000 of them. And you multiply this by this and divide it by this. Actually, divide it by the square of this, 10 to the minus 26, 10 to the minus 46, divided by the square of this. And then you will get and then you slide in time. You slide in time, here, here. You put your merger here, 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 here. And when you do it here, you get a lousy overlap, low signal to noise ratio. And then when you actually line up with the data, you get a peak. This is one of our Z of T's, and we have 600,000 of them. And in every one of them, we put a threshold at 5, let's say. And okay, so GST-LAL uses 4, and PyCBC uses 5 or 5.5, something like that. And if a peak rises above it, we record the time. We found the event. Of course, we might have also just found noise. If instead of there being a real signal here, there was a glitch here, well, you're going, you put your merger and ring down here. There's nothing, 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 nothing. Oh, here's a glitch. I now have a large number here. Even though there's nothing that matches it before the glitch or after, the glitch rings up the entire template and all the templates nearby. In fact, all the templates get rung up. And so you get peaks like this on every single template practically in your bank. Lots of triggers. Glitches are a pain, but we have ways of getting rid of them, as I will talk about. Here's a different way of looking at it. It's sort of animated. Slide your template. Oh, I slid too fast. So here's the template not matching very well. Here's the output, the magnitude of the match filter output. So you slide a little bit more, still no good match. Oh, here's a good match. I got a peak. And then it falls off again. So this is just a time domain version of the time domain filtering illustration. This is another way of visualizing. Here it is in the frequency domain. This is where we usually do it because it's much faster. Because what's happening here is that you have to do a convolution between the time, the data and the waveform template, and then you have to step many, many times. It's a convolution, and a convolution is slow. You have to do it many, 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 many times. It's slow. This is much faster, and you'll see why. It's because we can do it for all times by time shifting the template an arbitrary number of times with one integral, and that one integral is a fast Fourier transform, or an inverse fast Fourier transform, which we can do numerically really, really fast through clever fast Fourier transform algorithms. So that's why, at the expense of Fourier transforming the data and Fourier transforming the template, which cost computer time, this you can all do in advance. This you have to do once for a stretch of data, and you can take this product and this integral for 600,000 templates at the expense of one Fourier transform. Okay? In fact, you don't even have to Fourier transform the templates because many of our templates are initially defined in the frequency domain anyway. Those IMR phenom A, B, C, D, P template families, those are defined in the frequency domain already. So you don't have to even do this one. You'll have to do this one, but only once for 600,000 templates. And it's best to do it in the frequency domain because you know your noise in the frequency domain. You don't know your noise in the time domain. It's fluctuations in the time domain. But when you average over those fluctuations, in the frequency domain, you get a curve that can be stationary, the same now as it is tomorrow, if your detector behaves well. Okay? This is a very important thing, that doing stuff in the frequency domain makes life much easier, turns convolutions into simple multiplications of functions. That's what Peter Salson was trying to tell you a few days ago. Okay? Do things in the frequency domain. If you are an engineer, you know this already. An audio engineer, okay? You don't care whether you are listening to David Bowie or a soccer game. All you care about is that your response as a function of frequency is accurate, high fidelity. Okay? That's all you care about. You care in the frequency domain. Audio engineers don't care about things in the time domain. They don't want to care. They care about things in the frequency domain. And so do we. This kind of overlap can be by taking an inverse fast Fourier transform can be computed in the time domain very quickly. And if you take this quantity, the data, which is signal plus noise, against a template, matched filter it, get a time series out, divide by the normalization of the template, you get an SNR. You take the magnitude of this complex quantity, and what that does is this thing here has a real part, well, and so does this, a real part and an imaginary part. The real part is cosine-like, and the imaginary part is sine-like, and you're doing both at the same time. But the real signal is one particular combination. Cosine of omega t times cosine of phi. Phi we'll call the coalescence phase, plus sine of omega t times sine of phi. By taking the magnitude of this, you're automatically finding the peak as a function of phi. Does that make sense? You're throwing away the phi dependence because you don't care what it is. You just want to find the peak. You're optimizing or maximizing over the coalescence phase between 0 and 2 pi. Okay? And so compute this complex Fourier overlap, take its magnitude, you've automatically maximized over the coalescence phase, and then by finding peaks in time, you you are finding the maximum in time. Yeah. That's arbitrary. You can choose it as you see fit. And of course, you're going to choose a longer segment for longer templates. And what we do is Fourier transform we do one Fourier transform for all of our templates. So we make sure it's long enough to cover the longest template. And in the case of O2, 30 minutes. We make sure we overlap it because we may not catch the whole template. So we overlap it. We'll show you that in a minute. Does this all make sense? All right, here's another thing that's important to do. Remember I said that a glitch right over here could ring up this template with no signal to no signal power anywhere else. Sure. So to fix that, to reject those, we're going to say, I'm going to slice my template up into regions of equal expected signal to noise contribution to the sum. Maybe 10 of them. 10 pieces, and you can do that with long waveforms. It's harder to do with smaller waveforms. Chop it up into 10 regions of equal contribution to the total SNR. You can determine that in advance. And require that the contribution that the data give to the signal to noise ratio has that behavior. There's some SNR here, some here, some here, some here, some here. As expected, you can construct a chi-squared. Everyone here knows what a chi-squared is? Is anyone who doesn't know what a chi-squared is in this case? Let's just write it down. Write it down. It's easy enough. Chi-squareds In this case, it's really easy to see what the chi-squared does. It's a sum over these slices, okay, I equals 1 to maybe 10, okay, of the amount of SNR in slice I minus the expectation of how much SNR there might be. And this is going to be fractional, so fraction of the total SNR, expected SNR in that region, divided by the uncertainty or the noise fluctuations that would be in this difference, which should be Gaussian, squared, summum. That's a chi-squared. You can chop things up in a lot of ways. Here I chop things up in time. You can chop it up in frequency. You can chop it up in other ways, and I'll show you other ways to chop it up. And what it's doing is saying is that not only did I find a big peak with high SNR, but the distribution of SNR in time or in frequency is what I expect. Very powerful. If you do that for these kinds of signals, la-ti-da, you find this kind of behavior. This kind of behavior. The signal-to-noise ratio, okay, there's a okay, the signal-to-noise ratio is low, 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 low. Here's a peak. And that peak could be due to a signal or it could be due to a glitch. One way to tell. Here's the chi-squared. It rises and rises and rises. It gets worse and worse and worse. Very, very close. Okay? The chi-squared is lousy. Why is the chi-squared lousy? Very, very close in time as I time slide this. It's because if you time slide by a little bit, one wavelength, one period, or half a period, I should say, you get destructive interference, and your chi-squared is lousy. Every place where the signal should be positive, it's negative. Your chi-squared is terrible. It gets worse and worse and worse and worse. And then when they line up correctly within one period of that high frequency wave at the end, boom, the chi-squared plunges, and then it gets worse again. For a signal, for a glitch, the chi-squared is lousy everywhere. So what we're looking for is high SNR and low chi-squared. And we can combine them together into some kind of a measure of how good, how signal-like this is. And it's not just signal-like, it's loud signal-like. Louder than noise and signal-like. Okay? So we combine them together into a detection statistic, which is like an SNR, but it would be deeply discounted or hurt by having a big chi-squared, right where the SNR is high. Yeah.
So why is the chi-square decaying for?
Oh, because then it becomes just sort of random. Here it's random. Here it's destructive. Here it's like, the signal is pi away. So it's the signal and the template match, except with opposite sign, giving you a terrible chi-squared here. And here it's totally random. There's no, you're away from the signal and you're just got random fluctuating noise. Here it gets bad and here it gets great, right at that spot. And here's 20 milliseconds. So this is, by the way, what governs our time resolution. And you can see it's on the order of milliseconds. On the order of milliseconds. Not much better than that. Why isn't it much better? Why is our ability to determine where the peak of the waveform is in the data not much better than a millisecond? The frequency is about a kilohertz for a typical chirp, and so you're not going to get the time much better than one period, a millisecond. You'd think, oh, come on. In high energy physics, we measured picoseconds and femtoseconds. Why can't you do it here? Here's why. Of course, if we had a large SNR, not 10 or 20, but 10,000 or 20,000, we'd be able to do much better. Oh, it's 12:30. Okay, so I'm going to stop here, and we'll pick up next time. I'll talk more about how we do the match filtering in practice, and then talk about the big challenge, which is glitches. Okay.